Hello and welcome. In this lecture we're going to be talking about linear algebra fundamentals. These are some tools that will allow us to sort of formalize the analysis of linear circuits and generate a machinery by which we can put in values of currents and voltages into a matrix, and via some matrix operations we can find the desired results. So we're going to first begin by looking at systems of linear equations or simultaneous equations, which we've seen in previous algebra courses, and it is a prerequisite that we understand what they are and how we can find the solutions. Then we're going to learn how to represent these systems or these equations in matrix form, which is very important, is an important building block for achieving the goals that we're looking for. Then we're going to learn about what determinants are in linear algebra, as well as Cramer's rule. And don't worry about what it means right now if you don't know what it is. And after that we're going to look at matrix inversion, which is another method for finding solutions to these matrix problems. And finally we're going to take a quiz as usual to test our understanding. So before we go any further, let's recall what our main goal is here, our overarching goal. Our goal is to look at linear circuits and find the voltages across and the currents through various loops and nodes as defined in the KCL and KVL lecture. And so far we've looked at one of the passive components that we're going to be dealing with, which is resistors. But in the future, in the next few lectures, we're going to also look at capacitors and inductors. We'll look at resistors pretty in depth, in the sense that we look at the various ways you can combine them and whatnot. So after these few lectures, we're going to get into capacitors and inductors and more useful and more circuits that you would see more commonly in more sophisticated analog design. Okay, so let's review a very important building block, and that is systems of linear equation. In this case we have two equations and two unknowns. The unknowns are x1 and x2, which you can see they are scaled by some coefficients a1 and b1, and in the second equation by some coefficients a2 and b2, and they are equal to some number c1 on the top and c2 on the bottom here. So we have two equations and two unknowns, and if you recall from earlier algebra courses, if you have n equations that are independent of one another, and what I mean by that is, for example, they're not any one of those equations are not a scaled version of the other, they are independent. So if you have n independent equations, you'd be able to find n unknowns. So if you had, for example, I think it's pretty self-explanatory, but if you had, for example, 10 equations and 10 variables, x1, x2, all the way through x10, as long as the equations were independent, you'd be able to find all variables, x1 through x10. So the question here is, how do we solve for x1 and x2? If you recall from earlier courses, you had two methods, which were substitution and elimination. The idea behind substitution is to isolate one variable, and once you do that, you plug it into the remaining equation and find the other variable. For elimination, you subtract one equation from the other after you properly scale it, so you can cancel one variable out fully. And the goal there is also to isolate one variable and then do the remaining step and plug it into the remaining equation. So in this case, let's solve this example with two different methods, so substitution and elimination. So we have 6x1 plus 4x2 equals negative 14, and x1 minus 2x2 equals negative 13. We're going to first do substitution. So what are we going to do? We're going to solve for x1. So we're going to move this 2x2 to the other side, so we're going to add it to both sides to cancel it from this side on the left side. So x1 is going to equal negative 13 plus 2x2. Pretty easy there. And the idea here is I'm going to take x1 now, which I just found. I'm going to plug that into the first equation in parentheses, and that is shown here. You have 6 times that quantity, x1, plus 4 times x2 is equal to minus 14 or negative 14. So you distribute it through, you get negative 78 plus 12x2 plus 4x2 equals negative 14. You solve for, you combine 4 and 12, you get 16. You take 78 to the other side, and you get x2 is equal to 4. And you take the x2 value you found, and you plug that into the original equation you found here. So you get 2 times 4, which is 8, minus 13. That's going to give you negative 5. So we did it via substitution. Now let's do it by elimination. So I'm going to list the equations again here, and what I'm going to do here is I'm going to multiply 6 by R2 to scale it. When I do that, I get 6 times x1 minus 6 times 2 is 12, and 6 times negative 13 is negative 78. Then I'm going to take R1, which is equation or row 1, and I'm going to subtract 6 times row 2 from it. So I'm going to take equation 1 and subtract a scaled version of equation 2 from it, and what that's going to give me is 16x2 is equal to 64. If I divide by 16, I would get x2 is equal to 4. Then I'm going to plug that value into the original equation here, and I will find that x1 is equal to negative 5 also. So that these two different methods show us that we get the same answer. And graphically, if you'd like to see this, what you would have to do is first create some axes x1 and x2, and then we're going to solve x1 in terms of x2 for both equations. I'm going to assume that I'm going to think of x1 as my y-axis and my x2 as my x-axis, if you will. And once I solve these equations in terms of x2, I'm going to begin looking at each one of them and try to plot them. So if I look at the first equation here, if I plug in x2 is equal to 0, I'll be at this location. X2 is equal to 0, which is here, and that's going to tell me the value of x1. If x2 is zeroed out, that's going to be 2/3 times x2. So what I have remaining is x1 is equal to negative 7/3, which is slightly smaller than negative 2. And you can see that I've indicated that here. That's that 1 point there. And if you look at some other point, x2 is equal to 10, you could substitute that in, and you would find that it looks like I've deleted the values there, but you would find that it is this point at 10, negative 9 is what you would find. That would be the coordinates. So let me just write that. 10, negative 9 would be the coordinates. Let's just verify that really quickly. So x1 is equal to negative 7/3 minus 2/3 times 10. That is negative 7. Let's put everything over 3, and minus 20. That is negative 27 over 3, which is negative 9. And that confirms my y value, or x1 value, which is over here. So that confirms that. Then I draw the line here, and I look at equation 2, and I plug in x2 is equal to 0. So some special points that I can use as boundaries. So x2 is equal to 0 is going to give me negative 13. So I go all the way down here to negative 13. I draw my first point in orange. Then I'm going to plug in x1 is equal, or x2 is equal to, let's see, 5. What is that going to give me? x1 is equal to negative 13 plus 2 times 5. That is going to give me, that's a 10 there. That's going to give me a negative 3. So at the location x2 is equal to 5, I'm going to have a negative 3 is my y value, or x1 value. I plot that there, then I draw the lines, and lo and behold, I would see that they intersect at 4, negative 5, as we saw in the previous example. So what this is telling me is these are 3 different basic methods to find solutions to algebraic equations or simultaneous equations, and they really represent the same. From a system perspective, they're telling you if you were to assume that we have one system and each equation represents some subsystem or one component of the system, what it is telling you is that it is telling you what each variable should be such that the system is balanced in some manner. So for example, if you think in the context of circuit, we could have a situation where we have some voltage source or some sort of source, and you have some resistors, followed by another resistor and another type of source, either voltage or current source. And basically, if you were to apply a KVL here, this is just a very crude example. So if you were to apply KVL here, the first equation would represent this particular loop, and the voltage rises and voltage drops across each component, and how they relate to the current, and how they equate to zero. Basically, you would say minus the voltage here as you go up, plus the voltage here, and plus the voltage here, depending on the polarities you choose, but the idea is the same. You sum across their rises and falls, that should equal zero. In the second loop, you would say the same thing. You would say, you would go up and say, okay, sum this voltage rise or drop, sum this and sum this, and set that equals zero. And with your two different variables, I1 and I2, your goal would be to find the set of values for these two variables, I1 and I2, such that the system is balanced, so that the system is satisfied. In other words, you want to find a current where these systems connect correctly, and you have the correct voltages and currents through and across each element. That's the base. That's to get a gist of what this is telling you in the context of engineering and in the context of circuit analysis. We're trying to connect the abstract ideas in math to actual circuit or physics problems. Alright, so now let's begin talking about how to represent linear equations in matrix form. So the first question you might ask yourself is, why would I want to do such a thing, and why is that useful? So in practical situations, we're not going to be sitting around as an engineer or as a scientist and doing math on paper for very long, at least. We may do that initially, but eventually you'd like to let the computer do all of the grunt work, basically, to do all of the calculations that are just tedious and require a lot of time. So what we do is that, depending on the application, you would find some data from some experiment or whatever source it may be, from galaxies, from telescopes, whatever the data may be from any field of science or engineering. You would then turn this into some sort of equation. If you're lucky, these would be linear equations, to where you can say, okay, some coefficient times variable 1 plus some coefficient plus times variable 2, dot dot dot, and so on and so forth. So the only operations here would be multiplication and addition or subtraction. That's if you're lucky, we can do such a thing, or we can linearize the model. So if we do such a thing, if we can get the equations, we then want to be able to put that into the computer and let the computer do all of the grunt work, the tedious work. And we'll just want to be able to use the data that is calculated to do some useful thing. So that is the intuition here. We want to, or that is the motivation here, is we want to use matrices to be able to do these computations faster and faster. So if you look at this set of equations here, you can see that I have n equations, so, or in this case m equations. So the first index here on the left would be my number of rows or number of equations. So that's 1, 2, 3, and so on and so forth, all the way up to m as Mary. And if you look at the number of columns, that is my second index here, and that's going to be 1, 2, 3, 4, and so on until you get to n. So that is my number of columns. Now the sizing for the matrix then, or the equations, would be n would have to be greater than 1, and so more than one equation, and n greater than 1, so more than one column, or more than one variable, basically. Because otherwise that's a trivial case, right? That's just something times x1 equal to some number. That's very trivial. That doesn't require linear algebra or matrices. So here I'm saying m is equal to n. So why is that? So if you recall from a few minutes ago, we talked about if you have n linear equations that are independent of each other, so they're not scaled, so one equation is not a scaled version of the other, you would need n equations to solve for those n independent variables, basically. So that is why I'm saying m is equal to n, because you would have to have n independent equations to be able to find those or solve each one of those n variables. Now let's go ahead and put these equations into matrix form. So what am I going to do? I'm going to take all of the coefficients and list them in the same square shape, in the same format, and just plug them into this matrix here. And what I'm going to do then is I'm going to put all the variables. We can see that they're repeated everywhere. They're repeated everywhere, whereas the coefficients are not. The coefficients are unique. At each index there is one coefficient. Those are unique. But we can see that all of these x1, x2 through xn, they show up in every single equation. So why not let's just sort of factor it out, if you will, in a way you're factoring this out, and make it into what's called a column vector. And that is my column vector. It's sort of, the way I think about it is sort of a linear algebra way of factoring out, similar to a regular algebra where you factor numbers out of parentheses and whatnot. So we sort of gather this column vector here, and what we do then is, the way I think about what goes on here is, imagine that I take what's called the transpose, but we're not going to worry about that right now, but I would take the transpose of this column vector. It would look something like this. And this is just the way I like to think about it, so it doesn't, whenever I was first learning this, I use it to think about it this way so it didn't confuse me. So imagine that I just take the column vector and I just put it on its side. I make this column fall, I push it this way and it falls down. And if you do that, you can see that this lines up nicely over here, and I just imagine that I sweep this through to each single one and I just sort of multiply it out. So I would have the same thing you see up there, the same equations. So why am I saying this? So that's sort of what I think about to be able to understand what's going on here. So I'm saying that this matrix of coefficients, full of coefficients, multiplied by the column vector, which is which gives me the composed of the variables that I'm looking for. So this is what I'm really looking for, these variables, x1 through xn. That is all equal to another column vector, which is composed of some values now. So I had some matrix. It did something, it did some sort of transformation. It multiplied to this other matrix or a column vector, and it gave me a new column vector. And the sizing then would be m by n or n by n, because we said that's the condition. It has to be the same size. And the rule here is that for sizing is that for you to be able to multiply matrices, your outermost dimension for the first matrix and the innermost dimensions of the, or the leftmost dimension of the column vector or matrix should be equal. And we can see here that they're both equal, they're n. What does that mean? It means that the number of columns here should match the number of rows in the column vector. That's basically what that means. And you saw why, because it has to be the same number to be able to line up nicely and multiply through. So that is that concept. So now what are we doing here? What exactly does this mean, and how is this helping us? So there's this channel on YouTube that I really actually like. I saw it a few years ago when I was taking linear algebra. It's called 3 Blue 1 Brown. If you'd like more intuition, because I don't have the software or the linear algebra software or the tools needed to make such a thing, nor really the time nor the expertise, I would refer you to this channel and look at the playlist called The Essence of Linear Algebra. Essence of Linear Algebra. If you'd like more intuition on what's going on with linear algebra and matrix operations and whatnot, but the philosophy that I like there is that it shows you what's going on. And the way I like to think about these operations is that, okay, let's assume the fundamental premise of linear algebra, from what I see, the essence of it is that you have, let me draw this more nicely. So imagine that you have just everything's in 2 dimensions. So you have your x and y. But I'm going to call it I hat and j hat. These are very typical engineering and physics-based coordinate systems. So that's your x and y basically. These are unit vectors. So I should really be drawing this as such. So I should have an I hat vector here and a j hat vector here, which is in my y direction, if you will. So the idea here is that I have these what's called basis vectors, and let me just move these in. I have some space, I have a 2D space, and I have these basis vectors, I hat and j hat, and basically, just like a normal Cartesian coordinate system, I want to be able to represent any point in space via some value. So I by some linear combination. So for example, if I want to represent 3, the point 2, 3 here, what I would do is I would say, okay, let's multiply I hat by 2 and add it to, so let's say 2 I hat plus 3 j hat, and that's going to be my new point, whatever I want to call it, beta. So basically that's sort of what's going on here. You're scaling, you're doing linear operations to these basis vectors to be able to represent any point in space, and you can see that by simply changing the coefficients and the signs and just addition and subtraction, you're able to represent any point in this space. So now let's think about what matrix multiplication or linear transformations mean in this context. What would they be doing? How do they relate to these basis vectors? So the basic idea is that if I have some matrix, let's just first name these. So normally they, in a linear algebra course, they would name this matrix A. They would name this column vector here the variable x hat, or x put a vector on top, and they would name what's on the other side as these are vectors, these are column vectors, and A is a matrix. So what's going on here is that you have some matrix operating on a column vector, or just vector if you want to think about it like that, and that is equal to a b hat. So what's going on here is that you have a set of bases, a set of variables, and by applying some matrix to it, you get to a new location basically. So you can imagine that you have these basis functions, and you apply some transformation to them, and that transformation takes you to a new, takes each of them to a new location. You can imagine that that is what's going on. Let's just say that's this transformation. I'm not sure what that transformation would be numerically without actually going through it, but this is what would have happened. Actually, let me put it this way. So I would call this, this would have to relate to B somehow. So I would say, I don't know, B1 for example, and B2, each 1 and 2 being the columns, and 1 starting from left and 2 going to the right. So that's just some transformation there, and that is A. That is the basic idea behind what we're trying to do here. And if you were to and to find x, then you'd have to get the A inverse and apply it to both sides, and what you would get is that A inverse and A would give you the identity matrix, and that gives you an identity matrix with applying on x would just remain x, is basically, that's sort of like multiplying by 1. So then you would have x is equal to A inverse multiplied by B basically. So this is the way you would find the variable x, or the column vector x, is by taking the sort of going back from the operation here. So A works on A transforms x and moves it into B, and A inverse looks at B and applies an inverse transformation on B to take you back to x, to take you back to the original coordinates, and that helps you find what x is, the variables are. So this is not going to be a very comprehensive lecture on linear algebra, as I am no expert in linear algebra, and because there's more great works out there that I'm not going to try and recreate, because that becomes counterproductive given that our aim is learning circuit analysis. So we're just going to use the useful tools and that we get from linear algebra, and I will refer you to some inspirational or good sources that I've seen in the past, and the top one that comes to mind is 3 blue 1 brown. And Khan Academy of course needs no introduction, but I will write the name down just in case. Khan Academy. There's also Professor Gilbert Strang from MIT, I liked his lectures. Gilbert Strang. So here's just a few sources for linear algebra content if you'd like to know more. And again, we're not going to delve very deeply. We're only going to take what we need for circuit analysis, at least an introductory course. Alright, so now let's go ahead and look at some examples for multiplying matrices. The example here asks us to check if the matrices below can be multiplied. If so, we're asked to find the result for each multiplication. Before we even do that though, let's very quickly just go over matrix addition. The reason I didn't make a separate example is because it's so simple that I don't think it deserves an entire example onto itself. So let's say that I had some matrix 1, 2, 3, 4, and you're going to see that I'm going to use this sequence very often. And I wanted to add another matrix to it. So the idea here is that the dimensions have to be exactly the same for us to be able to add these together. Because otherwise it's not going to make sense for us to be able to add a matrix if the dimensions are not exactly the same. As you can see, we have a 2 by 2 here and a 2 by 2, so the rows there's 2 rows, so that's 2, and the columns are 2 as well. So the order is rows by columns. And you can see here rows by columns, and since they match, you would be able to add these together. And the way you'd add them is you take each corresponding index and add it to the value in that index for the second matrix. And you could also add many more matrices here if provided that they had the same dimension, 2 by 2, like this one. So in this case it would be 1 and 1, because that 1 and 2, because that is the index 1 1 for each matrix. That would be a 3, then you have a 2 and a 3 here. That would be a 5, you have a 3 and a 4, which is a 7, and you have a 4 and a 5, which would be 9 when added together. Very simple example, and that's why I didn't make an entire example out of it. So now that we have that out of the way, let's talk about multiplication. So in example A, we see this matrix, it is a 2 by 2, again rows by column, so there's 1 2 and 1 2 here. In this second column vector though, we can see that we have a 3 by 1, so 3 rows and 1 column. And if you recall, we mentioned that we have to have the inner dimensions here. The number of columns for the first matrix have to match the number of rows for the second vector or matrix, and for that reason, since they don't match, we can't actually go ahead and multiply these. Another way to think about it is if you tip this column vector over to the left, if you push it here and imagine that you're tipping it over, you see that we have a 1 2 3 here, and that's not correct because we have an extra number here, and that's not gonna that entry there is not going to be able to dimensionally match for multiplication, and therefore we cannot multiply these matrices. So let's say not applicable and /A. Now let's go to part B. We see here that we have a 2 by 1, 2 rows and 1 column, and on the second one we have a 1 row and 4 columns, so that's a 1 by 4. You can see that the inner dimensions match, and also additionally the dimension of the new matrix, the resultant matrix, would be a 2 by 4. That's the other fact that I have to mention here. So we know that we're going to have some matrix that is 2 by 4. Let me say equal here. It is going to be a 2 by 4, so 2 rows and 4 columns. So the way you know how to go about this is then you have to think that, okay, I have 1 row here, 1 entire row, and 1 column here. The way I would go about this is, given this dimension, for each row, I would go ahead and multiply this first entry here, the 1 1, multiply that through, and write the results down. So I have a 1 times 1, that's a 1, 1 times 2 is a 2, and so on and so forth here. As you can see, let's just multiply by 1. Then I go to the second row, and I look at the second row entry here for the first column vector, and then I go ahead and multiply that through by each corresponding entry on the second vector, and you would see that it's a row vector in this case. and you would get 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and 2 times 4 is 8. So that is the final answer in this case. And let's go ahead and move on to the third example. In this case, we have first let's look at the dimensions again. We have a 3 by 3 multiplied by a 3 by 1 matrix, or column vector, which is just a special case of a matrix. We can see that the inner dimensions match here, so that is good. We're able to multiply these, and the resultant matrix is going to have a size of 3 by 1, so that is going to equal a 3 by 1 matrix. Let me extend it because we have to do further operations here. So it's going to be a 3 by 1, so 3 rows and 1 column. Now let's go ahead and see how we would go about doing this. So the way this works is, again, you have to think that you're tipping this column vector over the second one, and it looks something like this: 1, 2, and 3. And imagine that I'm sweeping this through to each row, and I'm multiplying the corresponding values here: 1 to 1, 2 to 2, 3 to 3. And whatever I get there, I'm going to add all of them and put it into one index here, put it into one entry here. And that is why we have a 1 here. We have a 3 by 1, so 1 entry per row is essentially what we're going to have here. So I'm going to go ahead and go through this. So we're going to have a 1 times 1 plus a 2 times 2 plus a 3 times 3. So 1 times 1 plus 2 times 2 times a or plus a 3 times 3. The other way to go about this is you can think, okay, 1 times 1, 2 times 2, and 3 times 3. You're going to add the results for each and put them into one entry here. The next one is 4 times 1, 5 times 2, and 6 times 3. 4 times 1, 5 times 2, plus 6 times 3. And lastly, we're going to have a 7 times 1, 8 times 2, and a 9 times 3. 7 times 1, 8 times 2, and a 3 times 9. Now I'm going to simplify that into one 3 by 1 column vector, and that's going to be a 1 plus 4 plus a let's see, 9. That's going to be 14. Then I'm going to have a 4 plus a 10 plus a 18. So that's going to be 18, and 10 is going to be 28, and that's going to be a 32. And lastly, we're going to have a 27, a 16, which is going to give me a 43, and a 7, which is 50. Okay, so let's go ahead and talk about methods of solving linear equations.